Hello, KubeCon. It's really nice to see so many makers and builders in this room, so let's build some networks here. Thanks, by the way, Randy, for the introduction. My name is Zdarsky. I'm in Red Hat's CTO office responsible for edge computing. My background, though, is in telecommunication. I've been working in mobile networks at a large European telco provider. And this is the reason why I'm so happy to be here on stage with Raymond and have done this project together. Please, Raymond.
Okay, so my name is Raymond Knopp. I'm a professor in communication systems at a research institute and also a graduate school called Eurecom. It's in south of France, in Sophia-Antipolis. I'm actually also the president of the OpenAirInterface Software Alliance, which is an open source community for developing 3GPP software, and I'll talk a bit about that. When I come to a place like this, with a crowd like this, I feel a bit like a student because this subject matter for me, I'm learning it. I've been learning over the last couple of years from people like Frank and other people that attend these kind of events. Because actually I'm an expert in radio access networks. So it's really traditionally had nothing to do with Kubernetes or actually even cloud computing. But today it very much has something to do with that, and that's what we're going to talk about today. So what's all the fuss about 5G? I mean, you saw the keynote this morning, or many of you may have seen the keynote this morning. Looks pretty fancy, pretty expensive equipment up there. Really what it's about is ultra flexible radio access. And the term that the industry used is actually called 5G new radio. It's actually a very poorly chosen term because it's actually not that new. The radio is not that new, but that's what they called it. The objectives of 5G really are to boost bandwidth. That's one thing, but also the more spectrally efficient systems. I mean, especially in a place like the United States, spectrum is very hard to come by these days. I don't know if all of you realize that. But 5G tries to address that to make the systems more effective from the perspective of using the spectrum. The spectrum is very costly for the operators. And there are different ways of doing that. And basically one of the ways, it's a bit technical, it's called the bandwidth part. And basically what that is you take this big chunk of spectrum. The demo that you saw this morning was using 100 megahertz of spectrum. Compared to 4G, that's 5 times as much. Okay? And what they've decided to do was come up with a notion of the bandwidth part where you segregate pieces of the spectrum for different types of services. So what that means is when you start to do concepts like slicing high up in the network, it goes all the way down to the radio access itself with these concepts. So that is one of the things in 5G where they're bringing the radio access much closer to the concepts that you guys are using up in the cloud. And there's actually also very new abstractions for service classification which go really down to layer 1. Okay, so that's something new in 5G. The other big thing about 5G is the evolution of the cores, so the core networks. And what they've decided to do is actually keep the compatibility between the 4G and 5G cores with respect to the radio access. The 5G networks almost everywhere in the world today are deployed still using the same core as the 4G networks. It may be implemented using new paradigms in the cloud, but it's fundamentally the same set of procedures. That will change as time goes on. Now, the way they do that is something called dual connectivity, and I'll explain that a little bit. And also they use the term non-standalone operation. Non-standalone because the 5G network depends on the 4G network. Again, in that demo that you saw this morning, there was actually a 4G network there too. Right? It's fundamental. Now, the other big thing, and we'll talk less about that here, is because actually I'm not really very much of an expert on this part. The 5G core itself is now designed for a cloud-native architecture. Okay, the 4G core is now being implemented using a cloud-native architecture, but wasn't designed from the start. So they've put in certain aspects in the actual design of the core network itself so that it lends itself better to a cloud-native implementation. Okay, so what are the other things that are key about 5G? From the perspective of the 3GPP is the body that standardizes all the procedures that make up the system itself. 5G is 3GPP's answer to enabling new use cases. Almost everybody on the planet is using a phone that is running a 3GPP protocol stack today and radio. And there are a good number of Internet of Things types applications that are also using 3GPP radios. Maybe you don't realize it, but some of the credit card machines that you have in the restaurant, they're already using a 3GPP radio. It's a 2G solution, or a 3G solution. But now it's going towards the 4G and 5G case as well. But these, I would say, are the very traditional applications. 3GPP is now looking for non-traditional applications like industrial augmented reality, remote control. A fancy application is drones, but a real application is farming vehicles. Okay, we want to remotely control farming vehicles to optimize agriculture. That's a real application of 5G. And also the support for new vehicular services. There's something new, Radio V2X, which is very popular here in the United States and actually promoted by Qualcomm here in San Diego. That's really pushing this idea of advanced vehicular services in the 5G network. So this is all going to come, this kind of stuff. And basically, what they wanted to do is address requirements that are not satisfied by Wi-Fi or 4G-based solutions. Okay, so as you will see in what I'm going to talk about, the network density is going to explode. So there are going to be base stations all over the place. So you're going to need new forms of scalability. And you're going to, because of all of these new types of applications, you're going to need resilience for critical communications as well. So that's a very new thing in the 3GPP world, or in the commodity telecommunications world, this notion of critical communications and providing resilience in the networks for that. That's going to be a tough one, honestly. Now, if you look at the title that we put here, we talked about private 5G. Now, for me, we're going to be talking about open source communities that are building mock networks to be able to do some types of proof of concept like what you saw on the stage this morning. If there's one application that I can think of that is actually potentially an industrial application of putting the world of Kubernetes and 5G together in a small scale thing like you saw on stage, it's private 5G. Okay, and I can say that because today we're working very closely with one of our members, Fujitsu, who is a big company both in servers and in radio. They're working with our software for targeting this kind of a thing, still for 4G, but it naturally will extend later to 5G. So this is actually an industrial use case of what we're going to talk about today. And basically, you'll have the evolution of private LTE exploiting some of these new features that for these verticals. Okay, and ultimately, what you want is a customized IT and radio solution. So the judicious combination of the operating system, the servers, the radio, and the edge computing too, actually, for these types of applications. Okay. So what is here? Just a couple of slides. What a 5G network actually looks like. Now, up here on the top, what I'm trying to explain is where this is all coming from. If we want a really broadband system which has also extremely low latency, you heard that this morning in the keynote. Somehow that implies more bandwidth, both for the broadband part and the latency part. If you want low latency, you need a large bandwidth too. And if you have a large bandwidth, that means you have to go high in frequency, because in low frequencies, there's no more bandwidth left. In the United States, there's nothing left here. In Europe, there's not much more. And if you go up in higher frequencies, physics is going to limit you to have very short-range communications. So the type of equipment that you saw on stage today might have a range of tens to maybe 100 meters tops. Okay? They'll push it as technology evolves, but today that's about what it is. So these are not big cells; they're going to be all over the place. So if you look at the little picture that I drew down here, the 5G network is built upon the existing infrastructure. So you have your cell towers, which are covering a couple of miles radius, or maybe 10 miles radius even, depending on the frequency band. So one cell tower is covering a very large band. All the terminals, unless they're in heavy mobility, are connected to one cell tower. But now with 5G, you're going to add lots of small cells all over the place. And the way it's going to work, or the way it is working, is that basically you split the traffic into two types. The control plane traffic will go through the traditional cellular 4G type communication link, long range, and the high-speed stuff is going to go through your small cell. And that's actually what was running today on stage behind the scenes. So you're basically always in coverage with the 4G, and you get the super high speed, ultra wideband, the term that was used this morning, 5G, when you're near what they're called the G node B. That's the name of the 5G base station, the G node B. All right. Now this will evolve also. The 4G component will become 5G, but it will retain the same features of the 4G large range coverage. Okay. Now, the network itself, I won't spend too much time on this, But basically, you have two pieces in the network. You have the so-called core network, and you have the radio access network. Today, in the keynote, the core network, well, one of the core networks was actually running in Montreal, in Canada, or the control plane of the core network was running in Canada, and the user plane and the radio was actually running here in San Diego. So those two pieces were geographically separated, at least partially geographically separated. In France, we have it all in one data center, the core and the radio access. But ultimately, you have certain elements in the network which are there for the control plane, others that are there for the user plane, and yet another set of elements that are there to handle the radio access. Okay? So that's really what the network looks like. And you can see there are interconnections between almost all of these elements. The base stations are interconnected between each other so that they can communicate when you're doing a handover. And the core network entities are interconnected with the base stations so the traffic can flow in and out of the radio network. Okay, and there are all kinds of fancy interfaces that 3GPP specifies. Okay, so this slide here is really about OpenAirInterface. So this is the software that we've been promoting over the last couple of years. And actually also some of the friends that are doing similar kinds of software, not always in a community-based manner, but similar types of software. And basically it's all built on the premise that it's feasible to put a fully compliant 4G or 5G base station and the core network in a commodity x86 box. Okay, that's fairly recent. I would say in the last 10 years. We were trying to do it a long time ago, but it wasn't something that was close to commercial reality, let's put it that way. And today, actually, if you look, even major vendors adopt this approach. I was very recently looking at some of the equipment from one of our partners, Nokia. If you look at their G-Node B servers, you could basically just take the Dell server, take off the Dell logo, and snap on the Nokia logo on the server. It's the same thing. There's really no difference inside, except that they have maybe some types of hardware acceleration inside the servers. And that's why companies like Intel are promoting the idea of mixing x86 with FPGA on the same silicon, or at least in the same, on the same motherboards. Now, for the run-of-the-mill users like us, people that are doing proof of concept, today there is software out there. You can buy software, like a company like Amarisoft, which happens to be a French company too, that produces closed and commercial software for doing 3GPP, 4G, and now 5G also. You have our software that I'll talk about a bit, OpenAirInterface, which is open source. It so happens that it's also friendly to the 3GPP standardization process, which is a complicated thing in the open source world. You also have some code now coming from the ORAN initiative, which is an initiative of a bunch of operators that are getting together to try and influence cellular standardization and bring some open source into the world of cellular communications. These are both what we can call 3GPP friendly software examples. And there's another one which is really a traditional open source GPL-based approach by an Irish company called SRS, or Software Radio Systems. There's another one called OpenLTE. I don't know what the status is of that. These are both more traditional open source projects, but not necessarily community-based. Because at least from the perspective of SRS, they try and commercialize their software, so they can't really let a community feed into the code base itself. So with all of this, there's now an emergence of radio hackers out there, and development and user communities that are experimenting with 3GPP software implementations. And that's really where we stand here today. And in a nutshell, we have a sort of a democratization of the radio access through open source software, and even in some cases open source hardware, or at least open hardware. Right? So that's really the scope of this. Now, what we tried to do was put together a community that has some form of governance, and that actually encourages collaboration with the big players inside of 3GPP. Okay, that's what the OpenAirInterface Software Alliance is. It's like a traditional open source community, except when you're developing code that's running heavily standardized procedures, it's a bit of a trick to get the big guys that are making a lot of money on the actual standardized procedures to get involved in the community. Because if they push code into that, unless the licensing scheme is appropriate, they're going to lose their right to monetize their patents, which obviously they're not going to do. So OpenAirInterface is trying to address this. How do we put together a community that includes the big players in telecommunications today and still retains the methodologies and the spirit of an open source community? And you can see here some of our members that are actually feeding this, and you can see some of the, Nokia, Fujitsu, they're there. Qualcomm is there too, very recently. Other companies like InterDigital. These are all big intellectual property holders inside of 3GPP. We have lots of members like Red Hat and lots of universities from across the world, including several here in the United States, that are contributing now quite heavily to this. And we actually accept donations that are there to maintain an engineering support team for doing CI/CD, for doing community management and building, and also for managing the relations with all of these big guys in telecommunications. Right? So that's what OpenAirInterface is from the governance point of view. So let's go on to the let's build this component here. And I just want to acknowledge some of the people that are helping us, with the equipment part and with the software part. These are big European projects in 5G that are funding us very, very nicely, and also our partner Red Hat. We're very, very fortunate to work with Red Hat. We have access to a lot of the software tools from Red Hat that Frank is going to talk about in a couple of minutes here. So in terms of hardware, in the demo that you saw today, the equipment that was running in France is actually these little radio units here. These are completely open design, not necessarily by us. We put them together using open products. Inside there's a radio device called a USRP B200. It's worth about $500. It comes from National Instruments and originally from a Southern California company called Edis Research. And this can give us up to 50 megahertz bandwidth. You can do almost a low-end 5G system with this device. We put a little bit of custom hardware in there for the RF electronics so that you could actually transmit at a significant range. And we put a crowd-funded x86 board in there. It's actually called the UP board, which is a very low-end PC, which is there to allow us to experiment with the networking between the radio units and the cloud. Right, so this radio unit is connected by 1 gigabit power over Ethernet to the cloud to the data center at Eurecom. Right, so it's a very cheap device. Anybody could build it. Right, there's no secret in building this device. You could also build more expensive hardware. This is the hardware that we have for proper 5G outdoor deployment. A little bit different than the 5G that you saw on stage today. This is the 5G variant that you will have primarily in Europe, and to a certain extent here in the United States. The Sprint networks will have equipment a little bit like this, a little bit larger range, and in lower frequency bands than the one that you saw today. But this is much more costly, but it's still built on off-the-shelf components here. So we have the high-end USRPs, which are giving us 100 megahertz of bandwidth. This is going to cost tens of thousands of dollars to put this together, but nonetheless, you can put it together for a proof of concept design. And you could even find RF components. We found a small company in Hong Kong that provided us the RF front ends for this. Very cheap design and very, very efficient design for our needs. So this was completely built up off the shelf. A bit expensive, but completely configurable. You could also find production level hardware which is not from the big guys like Nokia, Ericsson, Huawei. Okay, very similar, but not. And why this is interesting, because some of these smaller equipment vendors, they provide equipment that can actually be seen as more or less commodity and white box, in the sense that you could connect it also to a data center. Right? The networking that's in these devices, they're radio devices, but it is generic enough. You run it off 2 times 25 gigabit Ethernet right to the servers, or right to the switch in the server room. And so I listed a couple of companies here that can provide this type of equipment, and this will give you something that is much closer to what is deployed in the field today by major operators. Okay, it's less generic and flexible than what I showed you before, but it's really ready for deployment in very specific bands. Okay, so if any of you are doing experimentation and you happen to have the right to transmit in an outdoor band, you could actually find equipment fairly easily to do that. So now I'm going to pass it off to Frank here.
Excellent. Thanks, Raymond. So we have this collaboration with Eurecom to actually help them provide real-time capable systems, help with the CI/CD flow in order to accelerate the development and delivery of OpenAirInterface. We've been collaborating in containerization, and of course recently, or currently, there's work in progress in order to basically run all the software development as well as a lot of the experiments with Eurecom's partner in the OpenAirInterface Alliance on Kubernetes, right? So just to give you a high-level overview of the deployment architecture, I don't want to go into the details of the individual components, but what's key here is that you see on the right in this box, there are these typical 4 core network components that typically are doing both the data plane processing as well as signaling or control plane processing, but they don't have the requirements to actually run real time. On the other hand, you have the eNode B, so the 4G, and the gNode B, the 5G distributed units, and this software has to run on real-time capable systems, right? And then to the far left, you see actually these USRPs, which are software-defined radios that are not on the cluster but are connected via the network. And another thing I would like you to notice is that there's a lot of different networking involved because, as Raymond showed earlier, all of these components have to heavily communicate to each other. They rely on multiple network connectivities. And you see that both of these qualities, and there are more qualities that are needed actually to run the software on Kubernetes, they are not like your traditional IT applications, right? So some of the extensions were necessary. In particular, you need to be able to provide real-time support. What does real-time mean? Real-time means determinism, right? Deterministic performance. And there's an engineering trade-off. You can get deterministic performance by trading off some other qualities like energy efficiency or trading off throughput, for example. But it's always a trade-off, right? In order to tune a system for real time, you really have to touch every single layer. You start really at the bottom of the machine. You have to tune your BIOS first, right? First thing is you have to eliminate any sources of non-determinism in your hardware and at the hardware and the firmware level. For example, disable the C states that transition you into different power saving states, right? The deeper state you are in, the more energy you save, but the longer it takes to actually wake up, and you don't have any control over that as a software. Similar with frequency scaling, similar with other characteristics. It's really hardware dependent, but you have to tune this because whatever non-determinism the hardware gives you, you cannot compensate for at the software level anymore. Going one layer up, next stop is the host OS configuration, right? So there are ways, of course, to set Linux to schedule with FIFO discipline and the real high priority. However, if you really want to build a real-time system, you have to use the real-time preempt patches for the Linux kernel. And then there's a lot of tuning going on. There's actually a tool called TuneD, which has various profiles to tune for various use cases. If you apply the real-time use case, it already does a lot of the optimization for you. And then, of course, you can do further tuning based on your workload. And as always in these real-time critical systems, at every step that you configure, you have to validate that you actually were effective in this tuning. Next step is you don't want to do this manually. So what you want to do is that Kubernetes does it for you. And so in OpenShift, which is the Red Hat Kubernetes distribution, what happens is that we use the machine API to declaratively configure not only which machines with which operating system, but also how to configure them. And so here you see, for example, a way to configure a machine for real time by specifying machine configurations that place specific systemd units onto the system and do some of the tuning that I showed on the previous slide. And then you create a mapping called that actually says, if your worker is supposed to be a real-time worker role, then map it to these configuration sets, right? And when you do this, every time you replace a machine, it's automatically getting reconfigured and retuned. Now, the next step is, of course, also on the kubelet level. You have to ensure determinism. And so what you need to do is to to ensure that your pods have certain guaranteed QoS resources, both on the CPU side as well as on the memory side. Both really go together there. Also important, if you want to ensure that you really get isolated workloads, I mean, your workloads use the cores exclusively, the real-time capable cores, you need to enable the static CPU manager policy, and you just see here the addition on how to do that. Another difference you saw earlier is on the networking side. Especially in the telco workloads, these workloads need multiple interfaces because you want to separate control traffic from data plane traffic. So traffic that carries user data from your management data in the cluster. And actually, the tool to do that is the Multus CNI. So here you see, for example, how we set up the networks for the GNodeB software running on the real-time workers. You have, of course, the default cluster interface. You have additional interfaces for the control traffic going to the mobility management entity, the user plane traffic going towards the packet gateway, and then eventually the internet. And then you have what's called the front haul, which is a dedicated network, high-speed network, connecting you to the radios. And if you want to do this kind of setup, what you need is to define so-called network attachments that say, if you attach to a network under this name, use this way of attaching, for example, pass through the physical interface, pass through an SRIV VF, or use MacVLAN or other techniques to do that. And then in your pod spec, you're basically putting an annotation where you're saying, I want connections to networks ABC, and these then appear as network interfaces 1, 2, 3 in the next step. Now, we've done this work together to actually take the OpenAirInterface software, containerize it, solve all the networking and security issues around that, then putting them onto a Kubernetes cluster. If you want to build this too, there's a lot of this configuration that has to go on. I didn't even mention all of them. There's PTP, time synchronization with high precision. There's FPGA support, etc. This is pretty complex to set up. Fortunately, there is a related open source community called Acrano. They built blueprints to make these kind of building of these stacks easy and scalable. And at this point, I would like to send a shout out to my colleague Yolanda Robla, who's leading the blueprint to create which we call Acrano Kubernetes Native Infrastructure Blueprint for vRAN that basically allows you to bootstrap this stack from zero. And also a special shout out to my colleague Ricardo Noriega, who's been awesome in helping us Kubernetize these software pieces. So you basically go to OpenAir Kubernetes GitHub repo. You will find the link in the references at the end of the slide. And then we currently don't provide pre-built images. Here are the commands that you basically need to build the images, push them to your cluster. And then the next step you need to do is adapt your deployment configuration because there are certain things that are specific to your machine setup. So for example, how do you find the software-defined radios, etc. This is what you need to do, and we use Customize to allow you to easily overlay the existing configuration on top of the default configuration. And then it's basically a matter of saying, customize build manifest of the whole stack or each individual components, say kubectl apply, and then this thing deploys. Shall we see a demo?
Okay. This is realizing it's kind of hard to do this in France, so we filmed something last week. And this, oops, I'm sorry. I don't see how to, that's here, okay. Okay, so this is actually a setup of the, I'm sorry, it's,
yep.
You take it out of screen.
Yep.
Okay, what we've done here, if you recall earlier, there was a picture of a rooftop installation. We've taken some of the radio equipment out of the rooftop, put it in the lab, so that we could control it here for this little demo. And it's just showing one component in the network, how you run it using Kubernetes. and showing also the standard compliance. We have a signal analyzer that's next to the setup, which is showing the integrity of the signal. This is something that we're using today in our lab to be able to test the conformance. Apparently, it's not working here. Yeah. Because the network is not connected. Just bear with me for 1 second. I'm sorry.
Just log into.
It's okay, but I don't know the password. It'll come up in a second.
The login password's cloud native.
You can use that.
Okay, it's here. It's here now. Now it should be okay.
Yeah, the other network would have been faster.
No, it's okay. All right. So here you can see the setup. Here on the right, those two gray boxes are the so-called USRPs. Those high-end USRPs that are usable for generating 5G signals. Is the terminal on top, which we're using to interact with the cluster that's in our server room. And you can see behind there those turquoise cables. Those are 4 times 10 gigabit Ethernet going to the server room, which is about 100 meters away. Right, so we're actually connecting. This is the equivalent of the radio units that were on the roof, and that you saw in Frank's diagram. On the left here, this is a laptop that we're using to act as the terminal. So what you're going to see here, that's the maybe Frank, you want to comment on that there? You're more.
Basically, you see the OpenShift console that gives you the ability to drill down on anything that's going on. In particular, of course, the resource consumption in this case. And all of your deployments, your config maps, even the machine configurations that you saw earlier. And at the end of the day, you basically start this command that I was showing on the previous slide to kick off the deployment of the. In this case, the core is already running, and we're basically adding the 5G base station here.
Okay, so you can see here normally the green light should go on. That means it's transmitting on one of the antenna ports. We're not using all the antenna ports here. You should see it come on. There it is. No, not there it is. There it is. Okay, now it's going to go over to the left, and you're going to see a device you didn't see at the beginning because we split this in 2 pieces. When the second time we filmed it, we didn't have the device anymore. It was on loan for a couple of weeks. So what this is showing basically is the signal integrity of the signal that's being generated by the cloud deployment of 5G. And the fact that you actually see very geometric figures there means that we are complying to the standard. And this actually is a laptop that's running a similar device down on the bottom, doing the same thing in a software implementation of the terminal. Right, so we're just showing the 2 things. One was with a commercial tester, and the other one was with OpenAirInterface terminal. The commercial tester just shows that it is fully standard compliant. I think that's the key message here.
All right.
So I think that's it, and we have about a minute and a half for questions.
Do we have time for questions? Excellent.